Hi all, this is lecture 24. We're talking about section 11.5 on alternating series test. So keep in mind, one of the things that we talked about when we defined sequences is that you can have a term that creates the sign change from positive to negative, negative, positive, negative, positive. And when that happens, when you have that, that's called an alternating series. So an alternating series is a series whose terms are alternately positive and negative. Now, of course, you can start with positive and alternate, or you can start with negative and alternate. So in our general form here, you can have negative 1 to the n times some subsequence bn, or you can have negative 1 to the n plus 1 or n minus 1 times your bn, okay? But keep in mind that when you take the absolute value of an and get rid of that alternating piece, then you have bn, okay? So when I reference bn, that is the absolute value of your sequence an. Okay, so what we do with this is we have something called the alternating series test. So that's how we test our alternating series for convergence. Now, what we need to look at here is two things. In order for our alternating series to be convergent, there are two things it must do. First of all, the sequence bn, the part without the alternating piece, has to decrease. Okay, so you have bn plus 1 has to be less than or equal to bn. And we've proved that for our sequences before, so that one's not new. And your limit as n goes infinity of bn has to go to 0. If those two things are true, then your series, and by the way, this was my typo, and I'll apologize, these should all be equal signs. Not sure how that got past me, but should be n equals 1 to infinity. Then your series is convergent. Okay, so let's take a look at the alternating harmonic series. So alternating harmonic series means we have a harmonic series 1 over n times negative 1 to the n. So that's the part that alternates. To show this is convergent, you have to show two things. Number one, you have to show that it is decreasing. And you're talking about bn decreasing. So bn here is the part without the negative 1, and that's just 1 over n. And so in order to show that it's decreasing, we need to show that bn is greater than or equal to bn plus 1, right? Just as we did before. So that's 1 over n, greater than or equal to n plus 1. Sorry, 1 over n plus 1. And in order to show that this is true, we're going to multiply both sides by n times n plus 1. And that's going to give us regular n plus 1 is greater than or equal to n. And if you subtract n from both sides, that's 1 is greater than or equal to 0. And so that's true. So it is, in fact, decreasing. The second piece that we need to show is that the limit as n goes to infinity of bn is equal to 0. So let's take a look. The limit as n goes to infinity of 1 over n is, in fact, 0, right? You get 1 over infinity, and that's equal to 0. So that one checks as well. So then by the alternating series test, this alternating harmonic series is convergent. Okay. All right, here's another one. Let's take a look at this one. This one that's not the alternating harmonic series. And so this one, what we have is we know that we need to show two things. We need to show that it is decreasing. So your bn in this case, without the negative 1, is 3n over 4n minus 1. And so what we need to show is that bn is greater than or equal to bn plus 1. So our bn is the 3n over 4n minus 1. Oh, man, I'm having trouble writing. Let's try that again. 3n over 4n minus 1. And we're showing that that's greater than or equal to, we'll replace the n with n plus 1. So 3 times n plus 1 in parentheses, 4 times n plus 1 in parentheses, minus 1. And that's 3n over 4n minus 1 greater than or equal to 3n plus 3 all over 4n plus 4 minus 1, so 4n plus 3. Now, if we multiply both sides by 4n minus 1 times 4n plus 3, we end up with 3n times 4n plus 3 is greater than or equal to 3n plus 3 times 4n minus 1. And I'm going to take that over here a little bit. If we multiply all of that out, we get 12n squared plus 9n is greater than or equal to 12n squared. We get 12n minus 3n, which is 9n, minus 3. And so if you subtract the 12n squared from both sides and the 9n from both sides, you end up with 0 is greater than or equal to negative 3, which is a true statement. So we can say without doubt that this is decreasing. Okay, next, number 2. And now you can see why we worked on showing things were decreasing, because we need them to show things like the alternating series test. The second piece, we need to show that the limit as n goes to infinity of bn is equal to 0. And so you have your bn here. You're looking at the limit as n goes to infinity of 3n over 4n minus 1. And if we take a look at that, that's infinity over infinity. So if you're using L'Hopital's rule, that's the limit as n goes to infinity of 3 over 4. So we get 3 over 4, which is not equal to 0. So this one will diverge, because it does not fit both pieces of the alternating series test. Okay, so that's the first thing that we want to do with our alternating series, is determine convergence. The next thing that we want to do is we want to take a look at estimating the sum. So we can use partial sums to estimate the value of the infinite sum. We can also determine the error in our approximation. Okay, so here's your alternating series estimation theorem. So if your alternating series converges, right? So let's say we've already proved that it converges. Then what we know is that your terms are decreasing, right? Bn plus 1 is less than or equal to Bn for all n. And we know that the residual for that n value, which is equal to the true sum minus the sum, partial sum, is less than or equal to Bn plus 1. Okay, so what is it that we can do with this information? Well, what we can do here is we can use the fact that our error, essentially, the residual is the error. So our error is approximately the same as our next term. Okay, so if we want our error to be within correct to 3 decimal places, so we want the error to be equal to 0.003 decimal places. Let's say we want that one to be correct, but this one can be off. Okay, so we want to be correct up to 4 decimal places. 3 decimal places, so I want 0.0001. Okay, so what I need to do is I can add up the terms until I get to a term that is smaller than this. Well, really, if we want it 3 decimal places, we want it to correct here up to this. So once I get smaller than that, so something with 3 zeros and then a value, then that number is smaller than this, and then I can stop with that value. Okay, so essentially it looks something like this. So we are going to start out with, does it converge, right? Okay, we're looking here at this one. Find the sum of the series, correct to 3 decimal places. So we're working with our Bn in this case is 1 over n factorial. So we need to show one that is decreasing. So this is 1 over n factorial. Has to be greater than or equal to 1 over n plus 1 factorial. And the way that we do this is n plus 1 factorial is n plus 1 times all the numbers smaller than it. So that's the same as n plus 1 times n factorial, right? N factorial is n with all the numbers smaller. So if you multiply that by n plus 1, you get n plus 1 factorial. And now if I multiply both sides by n factorial, I can get 1 is greater than or equal to 1 over n plus 1. Multiply both sides by n plus 1, and we get that n plus 1 is greater than or equal to 1. Subtract your 1s, and it's true for all n greater than or equal to 0. So that means that it's decreasing. Number 2, we want to know the limit as n goes into infinity of 1 over n factorial. And that means we get equals 1 over infinity, which is 0. So it converges by AST. Alternating series test. Okay, perfect. Now, what do we do now? Okay, so we're going to look at partial sums until we get to a term that is less than 0.0001, right? Essentially something less that has 3 zeros in it before the value. So let's see, our sum, let's start plugging in terms. So when you plug in n equals 1, and again, I did this all over the place. I'll have to fix this. This should be equals, n equals 1. Okay, if we plug in 1, negative 1 to the 1 is negative 1 divided by, and 1 factorial is negative 1. Then the next term, when we plug in 2, that's when negative 1 squared is 1, over 2 factorial is 1/2. The negative 1 part's going to alternate. You can start to see how that's going to happen. So 1 over n factorial is 1/6, plus 1 over 6 times 4 is 24, minus 24 times 5 is 1 over 120. And we can keep going here. So plus, by the way, you want to check to see what these are equivalent. So 1 over 120 is 0.008. So that one's not close enough yet. So let's go another term. So that's 1 over 720. So 1 over 720 is 0.001. That one's not small enough. So subtract, let's see, we're taking 720 times 7, and that gives us 50 over 40. So 1 over 50/40. And that one, I'm thinking that one's small enough. Yes, that one has 3 decimal places. That's 0.0001. So that means I can stop there. Okay. So I can stop there, and in fact, I can stop the step before that. So I can actually cut it off here. I can skip this one and just add up the other terms. So, I mean, adding one more makes it just slightly more accurate, but that's not going to change our estimation to 3 decimal places. So negative 1 plus 1/2 minus 1/6 plus 1 over 24 minus 1 over 120 minus 1 over 720 comes out to be negative 635. Okay. Okay, and so because we know by our theorem, our S minus S6 is less than or equal to B7, okay, from up here, right? S minus Sn, and I gotta correct this too. Oh man, look at me with the typos. This is Bn plus 1. That plus 1 is in the subscript as well. So the actual sum minus my partial sum with 6 terms is less than or equal to and that's the error, my 7th term. So I can skip the 7th and stick with the first 6. So 1, 2, 3, 4, 5, 6, and that's what we did. Okay, now we get into the idea of absolute convergence versus conditional convergence. Okay, so a series is absolutely convergent if the absolute value is convergent. Okay, so when we take a look at this one, you're looking at sum n equals 1 to infinity, negative 1 to the n plus 1 over n squared. So this is an alternating series, and we have n squared on the bottom. So we want to know if it's absolutely convergent. What we do is we say, okay, let's take a look at the absolute value. So sum n equals 1 to infinity, absolute value of this. And all that does is take off the negative 1 term in the top. So that's 1 over n squared. So what do you know about this series? Well, this is a p series with p equal to 2, and we know that this converges for p greater than 1. And therefore, if the absolute value converges, then we can say that this is absolutely convergent. Okay. So for example, not this one. I have this in the wrong place, I think. But that's okay. We can do it. The alternating harmonic series. Let's take a look at whether this is absolutely convergent. So we already said that it is convergent by the alternating series test. But if we look at the absolute value, that's taking off the -1 to the n, so that's 1 over n. And this is harmonic, which we know by the integral test diverges. So when the series converges, but the absolute value of the series diverges, we call that conditionally convergent. So conditionally convergent is when you have a series that is convergent but not absolutely convergent. So your alternating harmonic series is conditionally convergent. Okay. And here's a theorem that tells you that being absolutely convergent is stronger than being convergent. And so if you can show that it's absolutely convergent, then it's also convergent. Okay. Okay, so let's take a look at this example. So we can take a look at this. And so if we take the absolute value here, we know that the absolute value of this lies between 0 and 1. So this is less than or equal to 1 for all n. Or at least not our series, but the cosine of n over n squared is less than or equal to 1. Scratch that. Let's say this correctly. Whew, sorry, guys. The cosine of n here, the absolute value of that is always less than or equal to 1. So if I divide both sides by n squared, then this is true. So this one is less than or equal to 1 over n squared. And the sum, or the series, n equals 1 to infinity of 1 over n squared, is a p series with p equal to 2. And that's convergent when p is greater than 1. So this is convergent. So the absolute value of cosine n over n squared is less than or equal to a convergent sequence. And so by comparison test, then my series n equals 0 to infinity, n equals 1. I don't know where the 0 came from, of absolute value of cosine n over n squared is convergent, which means that the series n equals 1 to infinity of cosine n over n squared is absolutely convergent. Which makes it also convergent. Okay, so both things in this case.